Hello. Anybody hear me okay? Perfect. All right. So, let's see. Who's in the room today? Any data scientists in the room? All right, that's quite a lot. Engineers? Oh, okay, also good. Managers? One, okay, let's party. Today we're gonna talk about RAG, and I hope everybody understands what it is. Here's a little definition. Oh, sorry, not this one. We're gonna talk about this kind of RAG, which is Retrieval Augmented Generation, where we combine retrieval and LLMs together to improve its responses. Who here has a RAG prototype before? Okay, more than half the room, that's cool. Who plans to deploy them into production? Okay, cool. So this would be for you. So as we deploy these into production, we often realize that things that work well in a controlled environment doesn't usually translate that well into the real world. Going to production is never easy, and RAG apps are no exception. So this is where the aspects of security, scalability, observability, and resilience become important factors. So what we're going to do today is take a look into these challenges of deploying production RAG systems, and then discuss strategies to address these issues. And we'll begin with the first one, which is observability. So let's imagine that you and I have deployed a RAG app into production. It's in prod, and it's released to the wild. But then all of a sudden, after the launch, there's a spike in traffic, and it's clearly crashing. So we get a bunch of frustrated users. We get server errors, and no clear cause as to what is happening. So what is happening between a request and response, we have no idea. It's essentially a black box. What can we really do? As someone who's panicking, they might suggest, let's just print everything. But there are better ways to do that. And we can do that by instrumenting our apps to allow us to follow a request flow through the entire RAG stack. So we can do that with libraries. There are a lot of RAG observability tools out there. One example would be OpenLLMetry, which is built on top of OpenTelemetry. So the engineers in the room might have heard about that already. It's a library that allows us to track things like inputs, outputs, latency of each component within our stack. It also supports a wide variety of LLM providers, vector DBs, and so on. And more importantly, it takes 2 lines of code to set up, which is amazing for us efficient engineers. Of course, this is just one example. There are other libraries and examples like LangSmith, LangFuse, LangTrace. You get the idea. So as we monitor these metrics, there are a few that we would pay special attention to. And the first one, for example, would be error rate. So this is how often our system is failing and why. Hopefully, this will help us detect some sort of pattern so that we can investigate into them and prevent them from happening in the future. There's throughput as well, which is how quickly our system can handle requests. That would help us understand what sort of load we're handling and when they're coming. Of course, having visibility to these metrics would help us address any potential performance bottlenecks before it hits our users. In terms of accuracy, being able to see the inputs and outputs should be able to help as well. So we have got a whole bunch of metrics to monitor. What can we do else? What else can we do? It's not really efficient for us to sit around and look at it. So of course, we're going to set up some alerts that are automated. And the easiest way to do that is to set a threshold. And once that threshold is passed, an alert is raised, and we can investigate into that issue quicker. The idea is to address these hopefully smaller issues before it escalates into a bigger problem down the line. So of course, observability is just one piece of the puzzle. Let's look at scalability next. So we have set up some traces, and we take a look at what's happening in our app that has crashed. we realize that our app does actually not have concurrency support, which is a problem when you have more than one user using the app at the same time. So one thing to note here is that scale is quite situation dependent. So for the sake of the talk, let's say we have deployed our app in the wild, but we don't know if it's web scale or not. So what we can do here is if we have our own deployments, we can use a production-ready inference server. So these are specifically designed for production usage and that are able to handle multiple users, concurrent requests, and still support low latency. So these are examples like VLLM, which offers a great OpenAI API-compatible server, Hugging Face inference endpoints, which supports both embedding models and LLMs, and also RunPod, for example. So say we have one of these deployed in a single instance, we still don't know with absolute certainty how much traffic we're going to get. So the reasonable way to address this would be to dynamically add or remove resources depending on the traffic. And we can do that by enabling auto-scaling. This would apply to vector DBs as well. If you want to support higher query throughput by replicating your index over different nodes, or enabling higher availability for a system. And other than, in addition to horizontal scaling, we could also do vertical scaling. So we can add more power or resources to our existing machines. But bear in mind that there's only so much you can add before hitting a certain hardware limit. Another option we can do is caching by storing these frequently accessed requests and responses in memory. So that way, we can skip the entire stack through the embedding model, the vector DB, and the LLM. And that way, we can also reduce response time and server load. A final example here is simply to not give our users unlimited power by introducing a rate limit. That is usually controlling how many requests a user could send within a certain time frame, like per minute or per day. That way, we can prevent some abuse, distribute our resources evenly, and protect our infrastructure from being overwhelmed during peak loads. So now you might have a question. Why not just use an LLM API, right? They can handle all the ML ops for us. I won't have to worry about any of this auto-scaling stuff. You're right. But we're still subject to their rate limits, their outages. That's not too fun because that's outside of our control. Now, as we deploy to production, we also want to make sure that our system is secure and we protect our sensitive data. This is where security comes in. So let's say we inspect our traces once more, and we notice that user A's data is showing up in user B's responses. And that is not that good. That is not good at all. This is actually a serious security and compliance risk and a major headache for our legal team. Well, we got to fix it somehow. So what can we do here? Well, we could implement data partitioning. And this is isolating our users' data when we have all our data within one resource. And we call that multi-tenancy. Usually, this is a technique associated with lower cost because the resources are shared. And to help us understand this better, let's use an analogy with a building with tenants. So what we have now is a single server, single database, single collection with all the data. So we have one building, one floor, and no rooms. What's happening here is we have dumped all the data in this floor, and everybody can see everybody else's business. And there's no privacy there. What we want is to enable multi-tenancy, which is sort of like adding rooms to the floor by implementing partition keys. So that's sort of like adding room numbers to these rooms as well, so that when a user calls a request, it only retrieves data from that user's data. And of course, another way of increasing data isolation is creating an entire floor, an entire collection for each tenant. But that comes at a higher cost and overhead. So think about it as like adding stairs or adding elevators, that kind of thing to access different floors. Or there are more drastic measures like having an entire database within the node, sort of like within another building, within the whole neighborhood for each tenant. But that comes at a cost as well. When you have tenants that are idle, they're not using it, the resource is just being wasted. We can also add security to our LLM's component as well. Here, the goal is to avoid the LLM being hijacked through methods like jailbreaking or prompt injection. So an option we have here is use maybe a smaller LLM that we can prompt to classify the intent of the prompt, and then discard those that we think, or the model thinks, are jailbreak attempts. The trade-off here is that you get increased cost because you're prompting another whole LM. And the jailbreak attempt, that prompt might also work on that smaller LLM. We do have another option, which is to use a smaller classifier model. In this case, we can avoid that long latency as well at a lower cost. But we might suffer from some biases in its training data, which might not align with our uses and our task perfectly. So we could definitely apply more than one guardrail to our LLMs. And as we increase the number of guardrails, calling these sequentially would likely add up on latency, especially when we have requirements like that. One way to sidestep that is simply to call them asynchronously, along with your RAG-SAG as well. And one thing to bear in mind when we are applying LLM guardrails is that there might be a lot of false positives. And when that happens, we see a phenomenon of over-refusal of our system, which is not a great user experience. So this is especially true when the requests are benign and we're just simply rejecting it outright. But in any case, the adversarial attacks in LLMs is still quite an active field of research, so hopefully we get better solutions soon. So we have dealt with observability, scalability, and security, which brings us to the last topic, which is resilience, which is the ability to keep functioning in rougher conditions and handle failures and errors. So you guys have seen this before, yeah? Yeah. This is an unfortunate thing that might happen once in a while, and that is happening to our app today because our Cloud Vector DB has an API outage. And because of that, our system is not giving correct responses, and we have no other mechanism of delivering correct responses. So we have essentially created a single point of failure, and that is not great either. So what we can do is let's go back to our building analogy, if you may. Right now, we have a single building in a single neighborhood, and an outage is sort of like when the power goes out in the neighborhood. Our building is not going to work. Nothing's going to work. One way to go around that is, of course, have more buildings and more neighborhoods. And that way, if one neighborhood fails, the other one could take over. And in real terms, we are enabling an automatic failover while having multiple replicas. And of course, the added benefit of availability comes at a high cost because we're having these replicated resources, so it's like double, triple the cost. And when the money is tight, and it's always tight, what can we do? Well, we can simply try it again. So a retry mechanism is a super low-hanging fruit for any kind of transient error. So if the error is temporary, we can automatically retry, but this comes at a higher cost if we have a prolonged outage. The latency would just keep going. So we might need a different approach here. And another option for this would be a fallback strategy, so a kind of backup. This is where we can add a health check to the primary option. So say we have our LLM option, and when that fails, we trigger a secondary option. So what we have done today, short recap, is we have instrumented our prototype to trace metrics and monitor those metrics and set up alarms. For scale, we have used a production-ready inference server with auto-scaling, caching, and other things. For security, we have enabled multi-tenancy on our vector DB and added LLM guardrails. And for resilience, we have implemented replicas, and when the money's tight, fallbacks, and retries. So the journey, to production is always full of challenges. What we do next? We can always iterate, which is very important, as we continue to evaluate whether the setup is still important to us and is still addressing our needs, especially if it changes, and if your setup changes as well. But hopefully from the tricks we have learned today, which are not exhaustive list, we're able to build apps that are more observable, more scalable, more resilient, and more secure in production. And that's it. I'll be around staying for more questions, and if you'd like to connect, you can find me around as well. Thank you very much.